All right. Hello, everyone. Hello, Dong, Simon, Alex, Mitchell. Hello, everyone. Welcome back to our lectures. What is it now? Week 7, Wednesday. Hello, Tom. Tom's here as well. Hello, Tom. Today's going to be a what's the correct way of putting this? It's going to be a challenging, but hopefully interesting lecture, and it's also, I imagine this is a sort of point in the course where it's gonna pull back the curtains on in terms of there's some really interesting stuff in terms of why the ownership system and the borrowing system sort of is the way it is, because when you bring functions into the mix, mostly closures we'll be looking at in this lecture, there's some really interesting parallels between the ownership system and what you would want in and what you would want in to have sort of correct closures, which we're then going to bring into concurrency next week. So like this is very much a lecture setting up the groundwork. So when next week we bring in concurrency, it all sort of makes sense. We've got a good basis with functions and closures, yeah, it's really a point of sort of almost like culmination in terms of the whole borrowing system, and again why a lot of the design decisions Rust made in the language itself happen to sort of be the way that they are. So yeah. So are there any things we have to think about before we kick off with the lecture? Assignment 1 should have been due approximately an hour ago. I believe that's the case, an hour and 7 minutes ago or so. There was some questions on the forum around late penalties and stuff. The assignments, the weekly exercises, everything except the final exam follow the UNSW standard late penalty, which is the vague idea of a 5% mark reduction per day. So essentially, for each day you submit it late, you lose 5 marks. We are a little generous with that penalty in particular in that we calculate it hourly as opposed to daily, which, you know, on first inspection you might go, wow, that sounds worse. You're calculating my late penalty every hour? Like, why don't you just do it on the day? Well, if you think about it, as soon as you're 1 second late with the daily late penalty, you're already paying for like 1 day's late penalty. With the hourly one, we only make you pay that full 1 day's late penalty at the beginning of the 24th hour, I suppose. If the first hour is the second after it's due, that's the beginning of the first hour. Only at the beginning of the 24th hour do we make you pay for the whole day's late penalty. Otherwise, you'll only pay the 12th hour is half a day, you know, the 6th hour is a quarter of a day, and so on. Yes, imagine submitting your exam a day late and you only lose 5%. So yes, we can't have that one, but the assignments and the lab and weekly exercises are under that, what I would consider to be a relatively flexible system. Do recall, though, that the standard penalty also includes a flat 0 after 5 days. And we follow that as well. So you can only submit up to 5 days late without taking into consideration things like ELS or special consideration. So make sure if you do intend on submitting late and taking, you know, a small penalty for that, make sure it's less than 5 days after the due date, or we're forced to give you a flat 0. You know, everything else is as usual. You've got some weekly exercises. We've got the workshops tomorrow and Friday. Yeah, everything else is pretty much as usual. Any questions before we get stuck into our content today from anyone in the chat? Any questions? And Tom has broken the crab pyramid, I see. Oh no. Alright. So, functions. Hooray! We're going to start off this lecture by talking about function pointers. which is sort of like our baseline idea of talking about a function in sort of like almost like a higher up view, you could imagine. And it's also sort of starting to think of functions as what we'd call like first class citizens in the language, in that a function isn't sort of like a special thing that like special syntax in the language that can't be acted upon, but instead is something like an object that you could pass around and use in your code, like any other sort of piece of data or information. So most languages these days tend to have some form of capability for this kind of work, treating functions as values, treating functions as terms in your language. And Rust is no exception. And as we'll probably learn through this lecture, Rust is sort of very specific in how it chooses to deal with the idea of functions as objects in the language. And a lot of that comes from the difficulty in the ownership system and how that translates into functions. But it means that we get very robust functions as well, and it's pretty cool. So what's the idea here? Well, just to like kick things off, I could just say let my thing here equal to main, right? Main here being this function, and therefore my thing is now like a function that could be called. I could say then like call my thing like this, and this would just result in an infinite loop, right? So let me just demonstrate this. Hello from main. If I run this code, this is just going to be an infinite loop until it overflows its stack because it's recursive. So like our first sort of idea is that, I can use a function as a value here. I bind it to this variable my thing, and because my thing has this function type, I can then call my thing as if it were a function, because essentially it is at the end of the day. If I had another function, let's say some function add, takes in x as an i32 and y as an i32 and spits out another i32, and that just gives back x plus y, then I absolutely could say let my thing equals add, and then say println, say 2 plus 2 equals something, and call that my thing of 2 and 2. Run it, 2 plus 2 is 4. So our first sort of basic hello world example going on here. And the important idea is that this my thing here does have a type. I can specify the type. It looks a little bit like this. Right, so the type of my thing is a function that takes in 2 i32s and produces an i32 as a result. If let's say we had a function that didn't return, didn't have any return value, maybe it was just like print 2 numbers, something like that, and let's say in here it actually did print the 2 numbers out, then I could say let something with the type fn of i32 i32 be equal to print 2 numbers. Right, so the type here may include, like, if the function has a return type, then you'll have to specify that in the type. If the function itself has no return type, then you just omit that return type in the type. Similarly, let's say if you have a return type but no parameters in here, like say returns 42, that just returns 42 back, then the type would look a little bit like this. It would have an empty parameter list and it returns an i32. So note, you sadly cannot like omit the parens here and just have function goes to i32. You still need to specify there's no arguments in there, and that will be the type of this function pointer here, returns 42. Finally, the function that just does nothing, maybe it just says like print hello, produces some side effect, println hello, that will just look like fn, print hello, like that. So very first idea of using functions as like objects and variables and stuff like that in our code. Late class, ran out of time, program safety. Okay, cool. Yeah, so we're just getting started talking about functions and just looking at some basic function pointers in Rust. And if you're familiar with, say, Java has ideas around this, Python has ideas around this, C even has ideas, C++, all these languages. It's pretty rare these days to stumble upon languages that don't have any support at all for using functions as objects in some sort of way. Using objects as values, or sorry, using functions as values, or you know, functions as first-class citizens, whatever you want to call it. Great. So Rust has this as well. And as we've seen, the syntax looks a little bit something like this. When we're talking about the type, right? When we're talking about the type of a function, it looks a little bit like this. You write the word fn for the type, the parens, however many parameters, like the types of the parameters that it takes in. This could be empty, this could be one thing, this could be 100 things. And then optionally this return type on the right here. If it returns something, an arrow goes to the return type. If it doesn't return anything, then you just omit this whole portion in its entirety. So why do we want to start off with the syntax for specifying a function's type? Well, Rust is a very, you know, it's a statically typed language. You need to specify types everywhere. And so to end up doing anything, you know, there's small examples where you might not need to specify types anywhere, but to do most meaningful things, you're going to need to know how to describe the type of them. Like when we kick off this example that we're going to be working on through this lecture, which is going to be MyMap. And yes, C function pointer syntax. So this is also, I should mention, it's interesting. Let's say string from hello, right? Like the functions, all the function families, like type syntax is a little bit special in Rust. Like it's a little bit magic in that most types, you know, look like just like a word, like i32 or string, you know, just comprised of like letters and underscores and whatever. And there are some types that may contain generic type parameters. So for example, a vec of i32s might look like this. So some types also have, you know, generic type parameters, which have these angle brackets where you specify types in there. But these function types are pretty special in that they get to use things like parentheses and arrows and stuff like that. And this is sort of like a bit of a hard-coded idea into the compiler. And it's specifically to avoid really gnarly function pointer syntax that makes it hard to read. I'm quite a big fan of the fact that they did special case the types of functions in Rust, just because reading them left to right and having them sort of quite clearly split out is a strong preference for me, as opposed to, say, you know, Java with its like TR, you know, a function is a TR and a consumer takes a T and a producer produces an R. Like it, you could do all this stuff just with the generic type parameter syntax, that is to say. So like my thing, they could have made the language say it's something like an FN with return value of an i32, or, you know, like, you know, whatever. There's ways, different options they could have chosen. I'm personally glad that they took this approach, but it's something to consider when you're thinking about the language yourself, obviously. So to get back on track, we want to kick off this MyMap example. So throughout the lecture today, we're going to be working on the map, like recreating the map function. So let me get rid of all the cruft here for a second. What does the map function look like? Well, it looks like this. I can say create an iterator over some values. Let's say I have a vec and it's 1, 2, 3, 4, 5, right? And then I want to map over it. So I'll say let mapped equals vec. I'll turn it into an iter. I will map it and say for each x, I want to do, let's say x as an f64 multiplied by pi. This one, actually, let's do f32 because I don't want so many decimal places just clogging up our output, and then say collect that back into a vec. And then maybe I'll just finish off by printing mapped out like this. Cargo run. And you'll see I have like 1 times pi, 2 times pi, 3 times pi, 4 times pi, and 5 times pi. So map is a pretty awesome function in that it lets us take an iterator over any type, right? In this case, we've got an iterator over i32s. And then for each of those elements in that iterator, apply this function over it. right? In this case, we have a function that says take in an i32 and spit out that i32 as an f32 instead, multiplied by pi. So, you know, x times pi, I suppose. And note that the output of this function is also a completely different type. We didn't just have to go from i32 to some other i32, like +1 or +5. We could do that, but we can even completely change the type, right, of the things in this iterator, and then you know, keep doing other iteration stuff over it. Whether I want to say filter all the ones that are like, you know, I could say like filter where x is less than 10 or something, 10.0 rather. It's if x star x is less than 10.0, for example. There's all kinds of different things that I can do here. I can keep, you know, applying this iterator stuff, or I could even keep mapping over it if I'd like to as well. So we'd like to recreate this map function ourselves. And yes, okay, callable params return, void star function, void star int. Yes, there's some very, you know, every language makes their own decisions. I'm personally grateful for this one, but you are more than welcome to make up your own minds. So how do we get started with that? Well, we're going to start off with a function MyMap. We could sort of make our map as an extension onto iterators, like so we could just literally go .mymap right here. But it's not quite focused on exactly what we're looking for, so maybe we'll do that as an extension at the end if anyone's particularly interested. Instead, we'll just make a function that takes an iterator. So MyMap takes in some iterator, right? Iterator is a trait, so that's not quite going to work. And it's also going to take in like a function to like map over, right? And then we'll just basically call it, I'll leave the standard library one in here. It's not happy about that. I'll leave the standard library one here, but maybe we'll do a, maybe at the top, we'll do the code twice like this. And this will be standard is this, and my is that. And we're simply going to call, instead of like vec.into_iter.map, we're going to call MyMap of vec.into_iter and the function here. Right, the syntax is slightly less convenient, but it's effectively the same, and it'll let us see, you know, we'll run into the same kinds of challenges. Okay, so we've seen Rust's like function pointer syntax, right? How to sort of take a function in. And we've looked at traits and iterators and all that last week. So I'm gonna just sort of start, you know, kicking away on this one. So MyMap is gonna need to take in some, you know, some type which implements iterator, right? Iterators, we don't know what the type it is, like what the type of any concrete iterator might be most of the time when we're taking one in. Instead, we just want any type that implements that iterator trait. So I'm just going to make a generic type parameter here called I, and the iterator we take in will be that generic type I. And then I personally like to add in where clauses at the bottom here and do all the trait bounds and stuff in the where clause, but you could put them in, you know, inline right here if you wanted to, where I is some iterator, right? And finally, we want to take in a function pointer, right? A function pointer, which is going to map items from the from this iterator into like new items that may be the same type, but we want to create an API interface, you know, ATM machine, where we want to make an interface where they could be different types if the user wanted. So how do I specify that? Like, how am I going to specify this function signature here? Well, what we really want is a function from whatever the old item in the iterator was into some new item type, like this. Okay. So I can just introduce new type parameters for those, meaning this is some type here, that's some type there. We know is going to be an iterator, and there's one sort of additional thing that we want to include here. New item, that's fine to be realistically any type. Like, we don't care what the user specifies new item to be in a certain sense. But there is a restriction that we sort of need to place on old item, like a relationship we need to express. Does anyone in the chat know what this, or want to have a guess at what this, what kind of restriction we need to place on old item here. What kind of restriction do we want to place on old item? Or like kind of maybe like a relationship that we want to express in terms of old item. Collection, on the right track for sure. Old item, so old item itself doesn't need to be a collection, but it has a relation to the collection here that's being iterated across, which, yeah, Patrick's come across here is saying that, like, yeah, the iterator, the vec, yeah, the iterator items, we're all sort of converging on the right path here now. The type of item that the iterator is currently iterates across, that's got to be the same as old item, right? It's no good if we have a vec of integers and they give us a function that converts strings into a new item, right? This old item needs to be, whatever the, maybe old item's a bad name, maybe like current item is a little bit of a better name for it. And I can specify this here. Iterator has okay, Rust Analyzer is not playing ball with me. But iterator has this associated type item, like the type that the iterator iterates across. So I can use this syntax here by saying that the item that is specified in the iterator trait must be the same as current item, just like that. Great. So now we have an iterator I, some iterator where the item is, the item that's being iterated over can otherwise be known as current item. And a function that takes those current items into new items. Okay. All right. Now there's also one more like missing piece of this, which is iterators don't just we don't mutate an iterator that we're given. Instead, we give back a new iterator that applies this kind of transformation on it. I think we did a little bit of this. Maybe did a tiny bit of this last lecture with the vec iterator or the slice iterator. But essentially what we also need to add on here is a return type, which is like the type that can be iterated over. We're going to store this info in a struct. I'll call it struct MyMap. And we're just going to make this MyMap function give back a MyMap like this. And this is sort of the type. This is basically the type that is going to be held by the user, by the person calling this, that they can then continue to iterate over. So an important part of this is this struct MyMap. We're definitely going to need to implement iterator for MyMap, right? This is definitely to do here. We're going to need to implement iterator for MyMap. So what sort of state do we need to maintain in order to create this iterator that we're after? Well, we need, probably the most convenient is to just hold on to the iterator that they gave us and the function. And every time we call next on the old iterator, it'll give us a new item, and then we can apply the function on that and pass it out to the user. So I'm going to do that. I'm going to say the MyMap takes in the iterator, and it takes in the function, which was this new item, like that. I'm just basically following the signature that we've got here. So this is going to be given iter, and it's going to give in the function like that. But naturally, MyMap's going to go, I don't know what I is, I don't know what current item is, I don't know what new item is. So it's going to have to be generic over these types here, meaning MyMap, in order to create a MyMap, you need to have some type of iterator, some type of current item, some type of new item, like that. And this all seems pretty happy, but I need to actually specify the return type here. It's not happy down there, and that's why we're not getting an error yet. So I'm just going to reformat this a little bit, and this is going to give back a MyMap, like that. So we've got a bit of a gnarly function going on here, right? It's suddenly a lot harder to read, but it's got all the pieces we need. MyMap is generic over an iterator, current item, new item, takes an iterator, takes in a function, and returns back this type here, MyMap, which is generic over all these things again, which will eventually be able to be iterated over. So someone could just use it and then say .filter, .collect, whatever it ends up being. Okay. So now we need to implement Iterator for MyMap. Again, MyMap has these 3 generic parameters, right? The iterator, the current item, and the new item. And no matter, well, not quite no matter. If I wanted to say no matter what these types were, we can still iterate over MyMap, then I'll just basically do it like this. I'd say this implementation will be generic over 3 like random type parameters. I'm just giving, you know, these are just names essentially. For any MyMap of I, current item, and new item. Right. And then it's just saying, hey, you need to actually implement the trait items itself. So I can just say, sure, throw them in there and I'll fill them out. Now we've sort of got an implementation of Iterator going. We're going to have to like restrict things a little bit in a bit. But we can start to fill in some blanks and figure it out along the way. So if we're iterating across something that we've, we have some old iterator, and then we have a, we have a function that's mapping from the current items in that iterator to a new item that we want this iterator to spit out. What is going to be the type of the items that the map iterator spits out? Right? So this is a question for the chat. The old iterator we know spits out current items. Right, the old iterator is some iterator where the item is a current item. This MyMap iterator, what items is it going to produce? It's going to produce new items. Right, yes, that's right. So in here I can just say what the item that a MyMap iterator spits out is the type of the new item, which again we know this function maps from current items to new items. So that all makes sense. And now when someone goes, give me the next item from this iterator, how are we going to do that? Well, the way I'm imagining this is that we've got the old iterator, which is meant to spit out current items. We've got a function that goes from current items to new items, and we've got to give back a new item. Well, an option of a new item, but potentially a new item. So we could write something like this. Let the current item equals self.iter.next, right? This will be like some item or potentially none if we've reached the end of the iterator. Luckily, we can just bubble up this none. If this iterator is not giving us any new values, if it doesn't give us an item back, if it just gives us none, then we don't have anything else to give either. So we can just return that none back. Otherwise, the current item should be an item that has been spat out of the iterator. We need to give back a new item, and fortunately we have a function to do that for us. So I could say let new item equals self.function, and I want to call that with the current item. But note, this won't quite work. If I write self.function of current item, it's actually going to look for a function, like for a method called function, right? Like imagine Impl MyMap. Imagine we had Impl MyMap and some function called function, right? It's looking for this function here as opposed to thinking about the field. This is pretty common in a lot of languages that have this kind of syntax. I actually need to wrap these in parentheses to be like, hey, no, I don't mean this method function here. I mean the field. Once it's got the field, then call it. Then call it with the current item. So it's a little bit of like ambiguity there, and often you need to do this kind of thing when you're dealing with this stuff. Finally, we've mapped the current item into the new item, and we're ready to give that new item back. So I can say, here is that new item. Now, something's not going to work. I haven't saved the file. I've been very careful not to save the file yet, because we're going to get an error right here. Self.iter.next. What's it going to say? No method name next for the type parameter I in the current scope. Right? Ah, dude, the compiler is just too smart. It's just too smart. It's telling me exactly what I need to do, but I'm gonna drag it out a little longer, naturally. It's even pointing at this I up here, going like, hey, that's a little suspect. It might need to have an extra think about that. Essentially, what we've written here is that I want to implement iterator for my map with these 3 types being basically anything that you want. But that's not quite true. There's a restriction that this I here, I can't just be like an I32 or something. Or it can't be like a unit type. Or it can't just be just some crazy random thing. it specifically needs to be an iterator that produces current items. We specified that up here in the function that creates a MyMap, but we could also just make a MyMap directly ourselves, right? There's no sort of restrictions placed anywhere. So actually we need to add this restriction, as Daniel says in the chat, we need to assert that I is an iterator. Yes. So we will only implement iterator for MyMaps of I current item, new item, where I itself is an iterator that produces current items. So I can do that with a where clause here. Only implement iterator where I is an iterator that produces current items. Like that. And now this error goes away. Because, it knows that on self.iter, we can call any of the iterator methods on it, because we know it's an iterator, and it will produce something of type cur item. So that is fantastic. Loading symbol, it seems fine. I've got a bitrate seems happy. Might be a local thing. I think it's okay. I haven't dropped any frames yet, so that's good news. Yeah. So now we've implemented iterator for MyMap, and it does indeed map over this. Note that if we forgot to do the mapping and just spat out the current item, we'd obviously get a compiler error because it says, hey, I expected you to give back a new item, you gave back a current item. So we know the compiler's got our back, and so this means hopefully this works. So let's try it out. I've already got the code set up for my and standard library, and it does work. How about that? My and stood. That's awesome news. All right, so this is our first implementation here, and we're going to spend the rest of the lecture pretty much just iterating upon what we've started off with here. So I'm going to pause for questions, concerns, comments, queries, all of that, until we're relatively happy with what's going on here, and then we're going to move on to iterating on this design. There is one interesting thing, which I'm gonna preempt this question in the case that anyone might have it, which is I put the where bound here. I specified that I needs to be an iterator for MyMap to implement iterator, whereas I actually could have put that bound here, right? I would actually still need to have it here as well. But I could have put the bound on the struct saying that MyMap is only valid to exist in the first place where I is some iterator. Sadly, I can't then just leave it off the impl here because it's going to go, you said implement with any I for MyMap of I. It sees this I on the left-hand side as literally any type I. It sees this I on the right-hand side as an I to go into MyMap. And it goes, oh, MyMap requires that I is an iterator. You haven't expressed that this needs to be an iterator. And so you would still need to put this bound in here as well. Which kind of makes this bound here almost a little redundant. The only difference being you could conceivably construct a MyMap with some I that's not an iterator, and you would have a MyMap object, but you just wouldn't be able to iterate over it. Which again, that seems kind of weird. It's I'm going to put the bound here just so I don't ever run into that situation accidentally. And you honestly can. It's not really advised generally, in the community idiomatically. Just because if you have a type that holds a MyMap inside it, if I have a struct, has a lot of stuff, and one of those things, has a whole bunch of fields in here, right? Whole bunch of fields. And then one of those fields in there is some map, which is a MyMap of I, current item, and new item. Well, no matter what you do, you're going to have to bring these generic parameters across here. But if you specify these restrictions on the struct itself, you're also going to have to bring these restrictions up into the struct holding it. And then if you have a struct that holds this, you end up needing all that stuff again. And it's what the community would refer to as very infective, in that, sort of, generic restrictions on generic type parameters, trait bounds, are very infective when you're holding them in something like a struct or an enum. And so just to save a lot of that headache and having to maintain all kinds of crazy trait bounds when maybe MyMap has some other purpose. Like iterating is clearly its main purpose here, but maybe it has some other purpose. Someone does never want to iterate over it, but they just need it for some other reason. It's a little more flexible to only specify the requirements specifically where you need it, right? I only needs to be an iterator if you plan to iterate over MyMap, which is, this is sort of the take of the community. I personally generally align with that as well. Only specify the bounds where you really need it. Except, but obviously it's not really the case everywhere. I could actually leave off that bound here, right? This the bound on the MyMap, but I would tend to leave this bound in here just because it's not infective. This isn't going to infect any other items with this trait bound, and it's a good way of stopping the user from accidentally calling MyMap with something that's not an iterator and then being like, why can't I iterate over it? So it's every choice is its own decision naturally, and you got to think about them all individually. But that's sort of like some background on the thinking behind these kinds of trait bounds as well. Does adding the trait bound make it easier for Rust Analyzer? Over here, it makes it different for Rust Analyzer. Like it's semantically different, so Rust Analyzer will be able to notice that. But I would actually, I don't think it makes too much of a difference. If the trait bound is there, then anywhere you want to use it, you're going to have to, like the compiler is going to force you to put the where bound in anyway. Like the trait bound on it in order to hold the type. If you don't put it there, then you're going to get a compiler error, and you forget the trait bound, you're going to get a compiler error saying, hey, that method doesn't exist, you might need to add this trait bound, like we saw down here. Like the compiler actually suggested the exact correct fix. So I think it doesn't really end up probably causing much of a difference either way. But yeah. And what do I mean by infective? It's sort of like, it's specifically the case where adding this trait bound over here, right, over wherever, is likely to make other people have to put those trait bounds everywhere in their code as well. And having to manage that can be quite a headache. And so we generally try and avoid infecting other people's code with trait bounds. And the most infective places are things like putting a bound on like a actual struct definition here. Like I is something and current item is something, because if any other struct or enum ends up embedding your type in theirs, they end up needing to follow the restrictions that you placed in there. And if they have 10 types all with really crazy restrictions, they're going to end up with an essay just to define their struct. And again, it's also potentially limiting in future in terms of what you might want to do with MyMap. Maybe in the future, I think of a reason that, actually, I could be something else. Like maybe there's a different implementation of Iterator for MyMap where I is not an iterator, but it's something else entirely. Some other bound, and I still can implement Iterator for this in this case here. So putting generic names everywhere is already getting annoying. So it's something to think about, but it's a little more advanced. So I think we'll leave it at that, at that sort of level of detail there. But I'm sure you can probably Google away at Rust trait infectivity, potentially. Generic infection. Yeah, there's at least 2 articles or URLO posts. Yeah, generics are infectious, blah blah blah. So there's some interesting reading to be had. But again, a little bit advanced, so we'll leave it at that. Okay. Rust generics are better than C++ templates in terms of error messages, and right, that's just sort of coming from how the language semantically, defines these ideas, and the fact that they're more restrictive and more closely integrated into the type system, let's say, as opposed to sort of just raw substitution. Okay, so that seems all right. However, there is a limitation here. Limitation on function pointers, no environment. So what is no environment here saying? Let's expand our examples a little bit. And we're going to, what are we going to do? Let's say, I'm going to add in like another factor. And I'm going to multiply all the numbers by pi and also by this factor. Let's say like 2.5, right? In both examples. So x as f32 times pi times the factor. Right. So something strange has happened. The standard library, still perfectly happy, seems to compile, but our example is not happy, won't compile. So let's just comment ours out for a second and double check that it's not like swallowing the error. No, it does seem to work. So that's going to be 2.5 times pi. Maybe we'll change the filter to be less than 20 now. Yeah, so the standard library deals with this fine, but we do not. Oh no. So what's going on here? Let's do the same thing, less than 20. So this is where we are now finally going to get into this idea of closures. So what is a closure? A closure is basically, like a closure is just a function pointer plus an environment. Now, what is this weird, confusing thing, environment? It's basically, the environment is also often known as captures, like the closures captures. And I'm probably going to use these words a little bit interchangeably. But basically is there anything that this closure, refers to or depends on that comes outside of the like direct input to the closure? Yeah, external variables you might want to use. Absolutely. So notice that in this closure, loud bird. In this closure, the only variable, right? The only thing sort of in memory that that the function's using is x. It's input right there. Now you might go, what about pi here? Pi is just like a constant. You can imagine this to just be like a hash define, right? And so before we had factor, this was perfectly fine because it doesn't have any captures, any environment to it. But now we say, actually multiply this by factor, and factor is some like item, some variable, whatever you want to call it, that exists outside of the function here, right? In this case, it exists in main, but it could also, exist elsewhere as well. So in this case, this has now promoted from just being like a pure function pointer, right? Before, a pure function pointer is just like a function, these inputs, this output, whatever, into a closure. There's a function that can be executed and also, one or more captures from the environment, right? So the environment is the things around it. And in this case, it's capturing this factor variable here into the closure. So its captures are non-empty, means it's a closure, and the rules get more complicated all of a sudden. The rules get more complicated, so you got to buckle down and get ready for it. So factor is out of scope. External variables you want to use. Factor is lazily evaluated in the function. It's a good question. So that question is sort of coming from the perspective of how other languages might deal with issues that arise with captures. And in this case, it is sort of like lazily evaluated in a certain sense. But there's a whole bunch of extra rules that we're about to sort of like, plot our way through, which go like far past this idea of, just lazy evaluation and all that. Naturally, we're in Rust, so it all needs to, the compiler needs to be absolutely certain of everything going on and all that. Okay, so the closure syntax, so with function pointers, we know that we can have a function, like say a function foo that takes in an i32 and spits out an f64, I don't know, something like that. And we could just use this function as a function pointer, and there was syntax for the type of a function pointer. And this bar syntax here can also be used for a function pointer, but only if it has no captures, right? So only when it was in this case here. As soon as you bring a capture into the mix, it's no longer a function pointer. And so this was sort of, when we were at functions, we had functions like this, and we had closures like that. sorry, we had the anonymous function syntax, the lambda syntax, if you will, that look like this. With closures, you can do this. You can do the same. So you can treat this is a little tricky to sort of say accurately, I suppose. A function pointer must have no captures. A closure can have 0 or more captures. A closure with 0 captures can be treated as a function pointer. That's sort of like the cliff notes in terms of how these things relate to each other. So I could use this as like a closure if I wanted to, but almost always you're seeing closures with this syntax here. So, you know, bar x, y, z, however many parameters you want, and then the body of the closure. As we know, the body can just be like an expression, if you would like, and it'll implicitly return that expression back. Or you can use braces. Oops. Or you can use braces like such. And again, same sort of idea with the block. It'll implicitly return the last expression in the block. If you want to put a semicolon, now it returns nothing. It just returns a unit. Or you could say the word return, and this will also all do the same thing. So a few different ways of writing what is essentially the same code. I will leave it like this for now, because the most easily readable is, in my opinion, just in this scenario here. And the type of a closure is the next question. So before we saw this is the function pointer type syntax. How do we like specify the type of a function pointer? Now we're looking for the type of a closure. And let's see what Rust says. So I'm going to follow this example here. So let's say I had a closure that was like let x equal to a closure that takes in, say, an x and a y and gives back x plus y, something like that. Let's say x is an I32 and y is an I32 as well. What's the type of x? I like to use this trick. I specifically say that x is equal to a unit type just to sort of force the compiler to go, hey, the types mismatch. It actually is this type here. And this is where, I don't know if anyone noticed on the slides, it says, uh-oh. This is where the uh-oh comes in. The type of this closure is this thing in square brackets with closure at source main.rs 4417 4433. Like, that's the type of it. And this brings us to our sort of first big problem, which is that closures, the like concrete type of a closure is indeterminable, right? There is nothing I could write here that would be correct. It gives you the line number. Yes, exactly. So I could not fill in the type here, right? Like this type here, I could not fill it in with anything correct. I will always get a compiler error. Note that if I leave the type unspecified, it's fine, because the compiler internally can name the type, right? And we saw, again, just to reiterate it, we saw the compiler name that type like this, but we cannot name the type ourselves. What if you put in the line number? Like, what if we put in this here? Yeah, not a chance. So, so we cannot name the type, but the compiler can sort of reason about it internally. So that's a little worrisome, potentially, you know, what's going on here. And this is actually, you know, surprisingly, this is an idea that exists in other languages, not being able to name the type of closures. But it's something that we got to work around, essentially. So we can't name the type of this closure, sadly. However, they do implement some funky traits for us to make use of. So sadly, we cannot name the type of a closure. However, the unnameable type of that closure will implement some traits that help us use the type, right? Imagine like, think of it this way. When you write, you know, let's say vec of 123 dot into iter dot map of x is x times 2 dot filter on x is greater than 5 dot you know, I'm trying to think of other interesting things to do this, like dot zip, I don't know, zip with an iterator over 2, 4, 6. I don't know, I'm coming up with all kinds of crazy stuff here, right? You know, whatever, we get all the way here. How often do you think about what the type of this is? Like if I was to say let x equals this, do you really care what the type of x is? I doubt you do, because that's the type of it, right? It's a zip of a filter of a map of an intuiter of a thing of a thing of a that of a this, right? This is genuinely like I could actually type this out. Well, I'd have to get the imports right. But I could, in theory, type this. Well, actually not quite, because it's got closures embedded in it as well. But anyway, so it's got this really gnarly type. But we generally, when we're writing these kinds of functional chains, we don't care about the type. All that we care about is that each of these things gives us back some type that implements iterator. Right? The thing that really matters to us is that every time I call .intuiter or I call .map or I call .filter or anything like that, that function returns me back whatever type it is, however crazy it is, something that implements iterator, so I can keep calling more iterator methods on it. Right? This is sort of the primary idea that I'd like to sort of get into our heads here, because we can apply that same sort of thinking here. Sure, we don't know what type X is, right? We might not know at all what type X is, but if it implements traits that are useful to us, that can do the things that we care about, then we can probably still make good use of it. So in our case, this lecture, we're going to be looking at the 3 function traits, which are FnOnce, FnMut, or FnMut, I don't really care how you say it, and Fn, or Fn. Again, call it whatever you want, FnOnce, FnMut, 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 FnFun, like, I don't, whatever. But these are the 3 traits that sort of describe functionality, right? Closure functionality, whatever. And we're going to talk about how they work. And we're going to like play around with them. But yeah, I think we're maybe ready for a break, but just to outline where we're going to come to when we come back from the break. So these, when we define a closure, it's going to implement some of these traits here. We're going to talk about the differences between them all, you know, in the like the latter third of the lecture. But for now, we're just going to make use of this one here called Fn and ignore the other 2. And the idea is these traits all represent closures, right? Like functions that can capture from an environment, i.e. closures. So in our case, I could tell you that this X here does implement this Fn trait, right? This X closure here does implement Fn. In fact, this isn't even a closure at the end of the day. This could be a function pointer because it doesn't come from the environment. But let's say it was like X plus, let's say this returned an F32, and it was X plus Y times factor. I don't know, something like that. And it doesn't like that because this, it doesn't like, oh, right. It doesn't like that because this as F32, like that. So this here is no longer a function pointer because it captures something from its environment, but I can tell you for now that it will implement this Fn trait. And one of the most important ideas of these traits is that if you have some type T, or like, let's say some type F that we don't know, right? And F is some F. Right now we know, oops, wrong way. Right now we know that you can't do anything with this F really, because we haven't specified any restrictions on it. F could be literally any type. So there's just like anything I try and do with it is just not going to work. However, if I said that I placed a restriction on the type F that it must implement the Fn trait, it must implement Fn, then here's the real big important part. You can call it. Or let's say Fn that takes an I32 and produces an F32. Oops. Then you can call it if you give it like some 2 numbers in this case. All right, I can pass foo x here. Right? Do we sort of see like, I have never named the type of X anywhere here, because again, X has some insane crazy type. Here's the insane crazy type again. But I've been able to pass it to a function and even call it from that function without ever naming the explicit type of it, right? I've just said it's some type F, where F implements this trait that says this trait Fn of i32, i32 into an F32. And since I've placed this requirement on it that implements this trait, the compiler allows us to call it with the correct arguments and assuming the correct return type. Ret equals this, and we know that ret is going to be an F32. Right? Internally, it's calling this function here called call, which is, it's a little bit, strange and stuff, but it's essentially like saying f.call, but there's some special syntax on top of it, to special sugar and stuff to make this process a little easier. But you can imagine this is a trait that defines the idea of calling a function with an environment, essentially. In the same way that iterator is a trait that defines, iterating across some kind of sequence. This is a trait that defines calling a function with some captures, with some sort of environment. Okay. So when we come back from the lecture, I might try and spend a little bit of time talking about how this, what these sugars into might be a good quick idea. And then we're going to follow on in terms of refactoring this. So post any questions that you have so far, or especially with the stuff that we've just looked at here over the break. We'll come back at 5 past and we'll continue onwards. So yeah, think of any questions. I might even leave this code up instead of the usual break stuff. I'll just turn my webcam off here, which is here. And I'll leave this up during the break so you can have a look at it, see if you have any questions, and we'll come back at 5 past. All right. So, disassociate momentarily, and I'm very lost now. Let me give you the Cliff Notes summary of the, the last little bit here, the important bits, which is we're used to we're sort of happy with function pointers in that they can be constructed out of like some function, that you might write that just does some stuff, or out of this sort of lambda syntax where it just only uses the things that it's given. And we introduce this new idea of a closure, which is a function pointer plus some captures that come out of an environment, right? So in this case, capturing the variable factor. And so hopefully you can see that this is a sort of like a superset in that it can do all the things function pointers can do, but also more, in that it can read from variables that aren't defined inside it. It's something that you might want when programming. And we've sort of run into our first issue here, which is that the type of a closure with its, captures and everything is unnameable. We don't know what type it is. We can't actually write the type of it into our code. So instead, but fortunately the compiler will automatically implement at least, it'll implement a subset of these traits here on that type automatically for us. And using those traits, using those trait bounds, we can then end up calling it again later. So in our case, we're saying foo takes some type f. We don't know the concrete, the real actual type of f, but we're requiring that f implements this fn trait, specifically the fn trait of, an i32 and i32 and returning an f32. And with this trait bound, we can then call f as if it were a function with two i32s, and it'll give us back an f32. And again, the compiler implements this fn, fn or FnMut, FnOnce, these traits automatically for us. You actually currently cannot implement them manually yourself in stable Rust. You can in nightly, but it's all a bit tricky and stuff. So yeah, it does it all automatically for you. And we've essentially skirted around the fact that we couldn't name the type of this closure, using this technique, and we're going to make liberal use of this technique for the rest of the lecture. So random question, what is the meaning of plus tick static and where clauses for generics? It sort of in summary means that the concrete type, let's say it's some t is some trait, whatever, plus tick static, let's say, the concrete type t must not have any borrows that are shorter than tick static, that have a lifetime shorter than tick static. It's useful in sort of pretty specific scenarios, but we're also going to be talking about this tick static on, on generic parameters. In fact, tick static on a function parameter in next week's lectures. So I'll leave that one till there, or if you want a longer answer, you can ask on the forum, and I can give that to you sooner than then. And do closures set up the function call stack identically to normal functions, or do they do something special because of the whole environment thing? Right, so let me show you this now. So I'll just show you some quick, back of the napkin desugaring in terms of what this roughly looks like. But when I say let x be this function here, this is the way it sort of writes this code out in a certain sense. So the first thing it does is the compiler will generate a new struct itself. I'm going to call this main x closure captures, something like this. And you'll notice since I've used factor in here, it's going to borrow factor from main. So borrow factor is going to be a borrow of an f32. As we know in Rust, you can't just say in a struct, this is a borrow. We need to throw a lifetime on that, tick A. And so it generates this main x closure captures like this. And then it implements, in our case, the fn trait. Imagine just implement fn of i32 goes to f32 for main x closure captures of tick, of some lifetime. And then it goes function call with x as the i32, y as an i32, and gives back an f32. and it sticks our body in here, but wherever we called factor, it's going to sneak in self dot, oh sorry, I forgot the self in here. It's going to sneak in the self dot borrow factor like that. So, and then it turns this whole thing here, let x is blah, 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 into let x equal main x closure captures, where the borrow factor is a borrow of factor. This is essentially what it turns it into. I'll bring back the original code as well. So this is the same, essentially the same as saying let x equals, take in an x and a y, produce an F32 that looks like x plus y, oops, as F32 times the times factor. So the compiler is not going to like this. You know, I'm very sorry, compiler, but you're going to have to deal with it. But this is essentially what it turns it into. And that's why we can't name the type. The reason we can't name the type, like I didn't want to, you know, just give a reason that I couldn't really explain before, but now I sort of can say it. The reason this type is unnameable is because the compiler needs to generate it. Like the compiler needs to come up with a name for it itself. And so, you know, since the compiler comes up with that crazy name for the type, like we can't use it. We can't use that type ourselves. So the compiler's gone and done all this work for us. And it goes and does all this work in this specific way because it can leverage the existing type system in Rust. It can leverage the existing ownership and borrowing rules and all that. And we're going to see how that works. Okay, I'm glad. Okay, we're getting head explosions, interestings, making so much more sense. That's good news. All right. I guess maybe I'll leave this down the bottom then, if people seem to like this. Oops. Okay, cool. So, right, we've got some F that implements this, and then we can call it like that, and we're all happy. Okay. So, right, we want to make MyMap be able to support using an environment, right? Our problem here that we've got is that factor here doesn't work because this takes a function pointer, which function pointers are literally just like a pointer to a function. Whereas as we saw down here, if you're capturing stuff, you need additional data in order to like hold on to those captures, to be able to read those when the function is being called. And so if this is like, you know, some known type with a known size, how could I pass different functions, all that might have different captures in them, different amounts of captures of, you know, different sizes and all that, and like, you know, have this work? It doesn't work in short. Instead, we need to be generic over any type such that the type can be called. So we're going to introduce a new type parameter called F for our function, and say that it takes function is going to take in an F here, where I is the iterator and F is a function that takes in current items and produces new items. Right, so an additional little thing there. Naturally, we're going to have to change MyMap as well. IF current item, new item. And then we're going to have to, you know, keep changing all the way down to pass in this new parameter. F is a function of current item to current item goes to new item, like this. This is upset because it doesn't know this. Right, and now we get to this error which I was waiting for, which is that now it goes, hey, I don't know what current item and, like, you don't actually use current item and new item anymore. I don't even need to know what they are. And so, okay, we'll follow its advice, saying you don't use them, you don't need them. Okay, we'll get rid of that. We'll get rid of them over here. And the compiler is still happy. In fact, that's it. It's building again. And look, it's building with this. Right? Like I didn't remove that factor. Let me I'll just move this code down to the bottom here, where we're not gonna need it anymore. It now works. It's got the same result. So that was actually all it was just saying, no, it doesn't actually need to be a function pointer. It's just going to be this fn type here. Right? And so like, because this, we don't know what type self.function is, you know, some f here, right? But what we do know is we've placed this restriction that it must be a type that implements fn from current items to new items. And so we can call it. And it reads cleaner. Okay, great. I'm glad we like it. In fact, we could even take off, what could we take off here? We could take off current item as well if we really wanted to. If you're trying to like, you know, min-max the code you're writing here, you don't actually need current item as a generic type parameter, because current item is like specified through the iterator. So like watch this trick here. We don't need to be generic over current item anymore. And we'll just say I is some iterator, right? Forget about the item. And then the function, this is a neat little trick. The function needs to map from whatever the iterator produces to new items. And I can actually do that by saying, take the type I and, you know, treat it as an iterator. I have to write this I as iterator here because you could imagine I could implement a whole bunch of things. It could implement iterator, it could implement debug, it could implement clone, like all these different things, and I need to specify. Oh, okay. Connection was dodgy for a second, but I think it's all right. I just need to tell it specifically, hey, I'm treating I as an iterator here, and then grab the item, like whatever type the item is in that iterator. And I want a function from this type here, the item that the iterator produces, to new items. And this also works. You may not like this is genuinely like, if you might not like this, be like, that looks more complicated, even though there might be like less text, and that's perfectly reasonable. Or you might go, oh, I like that a whole lot more than having, you know, current item equals current item, blah, blah, blah. So it's your choice here. I'm not going to tell you what's right or wrong there. But it's an option if you're interested in it. And it is kind of a reverse turbofish, yeah. Where is the function trait? I think it's fine. Where is the function trait defined? It's defined in the standard library. FN. Nope. Yes. Trait stodops FN. And it's like a little bit gnarly. You're not meant to use this trait directly, right? You're meant to use all the sugar on top of it to like deal with it. But there is progress that's being made over time to help users use this trait directly if you would like to. But it's just not like, the language isn't quite at that point yet. But again, Rust is a language that's very iteration happy. It's very happy to like put something out now that we know we can commit to, and then slowly improve it over time. So the language will get there, but we're not quite at that point just yet. All right, so that's pretty cool. Let's bring in our next problem. Back to MyMap. Okay, no, I'm going to run us into the problem first before we move on to that next slide, which is watch something else that the standard library can do that we're not quite good enough at. So let's forget about this stuff for now. I'm going to write a slightly different example. And this example is going to be like, let greeting equals a new string. I'm going to say grab a line from standard input and put it into the greeting. Let's call this, I'm going to do something in a second. So I'll call this line, and then I'll say let greeting equals trim the line, because it, you know, brings in a new line off the end and all that, which is kind of annoying. All right, this is going to return a result, so just forget the result. You know, panic if it goes wrong. And now I have a greeting from standard input. Now I want a list of names. So this is going to be like some common code up here, I suppose. A list of names. I'm going to do, okay, who's in the chat? We got Miguel, we've got Mitchell, we've got Patrick, we've got Dong, and I remember Tom was here earlier. We'll throw Tom in there as well. So we've got a few different names. And now I want to like iterate over them and do something a little fancy. So I'm going to say, let greeted equals names.intoIter dot map these names into, I'm going to use like a body here, and then just collect them back into a vec, and then print out my map is greeted. Okay, great. And what am I going to do in this map here? I'm going to do something pretty cheeky. I'm going to say let mut nth equals 1. And then say let greet name equals number nth is a greeting for the name. Yep. Nth plus equals 1, and then give back that the greeting for that name back to the map. And this could be return, greet name, whatever you prefer, but this is just very slightly more idiomatic like this. And this should not work, but it seems to be compiling. Did I do? Oh, I did. This is the standard library ones. Okay, great. Sorry, this is stood greeted. I was like, what the heck? Why is our code like working? That should not work. And I'm going to paste it again for MyMap, and I'm going to swap out names into it a map for MyMap of names.intoIter into iter, and the function is going to be this function here, like that. Okay. So this is MyMap here, and this is the standard libraries map over here. So let's just comment out mine for a second because it's not compiling as I was hoping, and see what the standard library does. So it's going to wait for us to type in some greeting. So I'm just going to do like hello there. And the standard library spits out number 1, hello there, Miguel. Number 2, hello there, Mitchell. Number 3, hello there, Patrick. So on and so forth. Right? So it, it assigns like the number that it's the nth person that it's greeting. And specifically, it's like mutating that nth there at the same time. Right? So that all seems, well and good. But suddenly when I uncomment this, I get an error on this line. Cannot assign to nth as it is a captured variable in an FN closure. Okay, so it really doesn't like the mutation on this nth. And we've all been using Rust for this is our 7th week now, right? Rust is like pissed off about mutation. Like, what's new? You should be pretty comfortable with the idea at this point that like Rust just gets pissed off when you're trying to mutate something a lot of the time. And this is just this again. So something's gone a little wrong, and we're going to get a little bit more background. So as an aside to help us think about what we're about to learn here, we're going to recap like the ownership system. So consider the idea that we have like a struct foo, which just, I don't know, has some stuff in it, whatever. And we implement some methods on foo. We implement a function foo owned that takes self, foo exclusive that takes an exclusive borrow on self, like a ref mute on self, and foo shared, which takes a shared borrow on self or ref self. Right? And it doesn't really matter what else they do, but like these are the function signatures here. What are the restrictions on calling foo owned, foo exclusive, and foo shared? Right? So imagine I've created a foo, right? I've created let foo equals some foo, whatever. And I want to call some of these functions. Let's start off with foo owned. What's like a restriction that we might think of in terms of calling this method here foo owned? To be clear, I'm going to assume that like all these functions I can call at least at least call those functions once. But so Daniel notes that it transfers ownership of self, right? And so Simon is pointing out exactly what I was looking for here, which is since given it transfers the ownership away, as Miguel says, it needs to take ownership here. It sort of implies that you can only call foo owned once, right? Like I have a foo. If I want to call foo owned, I can only call it once. Does that make sense? Like in terms of if I tried to call this function 2 times, the compiler would give me an error and say, hey, when you called it last time, you actually moved out of your foo. You transfer the ownership, away into that method call. So therefore you can't call it again. You don't have ownership anymore. Does that principle make sense? Okay, cool. And that also points out we've got about like probably a 10 to 12 second delay, or 10 to 15 maybe. Okay, we're happy with that. Now let's get on to foo exclusive. So what are the restrictions on calling foo exclusive? I'll get us started. We need like exclusive access to self, right? So it requires that we can take an exclusive, we either have an exclusive borrow on the foo, or we can take an exclusive borrow on the foo, right? So like that's our requirement. But what does that sort of imply? Like what real world restriction does that imply? And this is kind of like a tricky question for me to ask right now because I'm sort of predicating this a little bit on what you might find out like next week when we're really playing around with concurrency and stuff. But yeah, so that function sort of like kind of like owns self for the duration of that function. Yeah, so for the duration of that function, it must be the only thing with access to the foo is a nice way to put it. So you can't have a shared borrow, you can't have another exclusive borrow, anything like that. For the duration of foo exclusive, it needs exclusive access on self. Nothing else is allowed to possibly access self while the function is, running, while that function is being called. So one of the restrictions you might think of is that you can't, like you can call this function, the previous one you could only call the function once and then you're done for. For foo exclusive, you can call it as many times as you want, but those function calls can never ever be overlapping. Right? In terms of, let me grab, oh gosh, I hope this works. Yep, it seems to work. In terms of, if I was like calling, the exclusive function and it took this amount of time and then the function returns back to me. So I call exclusive, it starts running, and then it finishes and it returns back to me and I keep going, then I can go like, okay, call exclusive again, and then it comes back and I say call exclusive again, and that's all fine. But we can't ever have something like this, right? Where we're calling exclusive and as it's running, it's like overlapping with another call with that same borrow, right? Calling exclusive with that same foo at the same time. Now, Dong is absolutely right in mentioning single threaded here, because this is a very tricky, it's a very tricky situation to run into when you're single threaded. It is technically possible with something called continuations, or like async await, as Mitchell points out here. Async also comes into this, but very sadly, it makes me very sad to say it, it's a bit too much for this course. It's like too hard for us to bring in from at least what I think for this in terms of this offering. So it's pretty rare to run into a case like this on a single thread, but next week when we bring in concurrency, when multiple threads can be acting at the same time, this is dangerous, right? This is no good. We can't have two functions. We can't have it like overlapping and call, because we'd have two things with exclusive access at the same time, essentially, which goes against the whole point of exclusive access. And then we have foo shared, right? And foo shared, what are the restrictions on that? Well, we can definitely call it once. We can call it more than once. We can call it as many times as we want, like foo exclusive. But also, we can call like foo shareds all overlapping with each other at the same time. Like, that's all fine. The one restriction, as you note, is that we can't have, someone else with exclusive access, right? Like, no one else can be mutating or taking ownership of it or anything like that. You're allowed as many shared borrows as you want, and they can be all occurring at the same time and doing the same stuff. But nothing else can have exclusive access or ownership, or like, let's just say exclusive access or transfer the ownership away while we're borrowing that, while we have that shared borrow. Right. And also you can almost imagine like, so we're saying, oh, no mutation can be done. And that's absolutely true. There's also another point though, that's like, that's more of like a restriction on mutation itself. You could also consider that as like, it's not really a requirement that in order to have a shared borrow, you can't be like mutating it at the same time. But in order to mutate, you must have exclusive access. Nothing else can have access if you want to mutate. So it's perfectly fine to consider it to be restrictions on both of them, or you could also just consider it a restriction on a mutation, on an exclusive borrow. Okay, so we all seem up to speed on this, pretty much. And now we get hopefully a bit of another brain explosion moment. What's this? Oh, we've already seen this. So we saw that we can specify the trait syntax like this. And there's also, FnOnce and FnMut, which we're about to have a think about. We've just looked at Fn, but there's actually two other things, FnMut and FnOnce. And what these trait bounds mean in terms of some closure implementing these traits, FnOnce will be implemented on a closure that can be called once, right? And that's every closure. If you cannot call your closure even once, right? If your closure cannot even be called once, it probably doesn't deserve the name of a function, right? It's a nice quote from what's his name? He's a engineer who works in New South Wales actually, and was a previous Rust team member. I will remember the name, and I'll try and post it, or I'll mention it in the next lecture or something. But yeah, he's got some fantastic articles on closures as well. But yeah, FnOnce means it can be called once. Every closure implements FnOnce. Now FnMut, that's implemented on a closure that can be called indefinitely, as many times as you want, but can never be called simultaneously. Not Tim McNamara, actually, someone else. So it can be called as many times as you want, but never overlapping, never simultaneously. And then Fn can be called indefinitely simultaneously, right? This sort of does this ring a bell to what we were looking at a little earlier, right? Hopefully it's ringing a little bit of a bell. Now, how can it determine what which ones it can if something can only be called once, or if it can be called indefinitely but never simultaneously, and so on and so forth? It's determined by an FnOnce if a closure moves something out of the environment into its captures, right? If it actually moves a variable that exists in the environment, right? So there's a variable here, let's say greeting, and it actually moves it into the closure, then that can only be called once, right? That can only be called once because the first time, it's moved it away, it's put it into the closure, and so you can, then use it there. The second time, the second time you try and call the function, there's no more thing to move out of, essentially. So that's a little dangerous. FnMut is the closure only captures shared and exclusive borrows, right? So references to the environment. It doesn't move anything, right? There's no moving going on that could be a little scary. I think I might need to retcon this slide a little bit. I think it's actually slightly inaccurate when I'm saying it out loud in front of the lecture. But I'll have to have another quick think about it after the lecture again. But it's close enough for us now, I'm sure. So right, an FnMut, there's no sort of ownership problem going on here. It's only dealing with shared and exclusive borrows to the environment. And an Fn only captures shared borrows to the environment, right? So it's only reading with shared borrows from the environment. And this almost basically perfectly corresponds to the ownership system in terms of self, exclusive borrow on self, and a shared borrow on self. Right, so if we think about the requirements and the cases that you're running into, well, this is, Fn is only shared borrows, right? Shared borrow on self. FnMut is shared and exclusive borrows to items for @mut self. And ownership is, transferred through self in the example that we saw before. Furthermore, can only be called once, is tied to self. Can be called, indefinitely but never simultaneously, @mut self. Can be called indefinitely and simultaneously, is a shared borrow on self. It all sort of lines up with the ownership system. So this is what I was like just putting together there, is that if you have some type T that you have, self at mute self and shared self, then, these are the restrictions that we talked about in terms of those. On a function trait, it's essentially the same things. It's the same ideas, but applied to functions. And so it actually ends up using the exact same ownership in order to enforce these ideas on functions. So let me just see what the chat's saying. I'm guessing after an FnOnce is called, that environment variable is moved back out into the original environment. No. So it actually doesn't. There's some kind of technical reasons for it. The short answer is that if you have a closure that's moving something out of the environment, it's perfectly conceivable for that closure to outlive the environment. So you actually wouldn't want to force it to transfer it back into the original environment. Whereas with borrows, it always needs, the environment must outlive the closure because you're borrowing from the environment. Yeah. So but a little technical, a little deep, probably the course forum for that one. I thought it'd be consumed by the closure, whereas FnMut would return it afterwards. Yeah, and that's sort of how the borrowing works there. Yep, for sure. So if we do something like let message equals greeting in the closure, that is FnOnce. So that's a really good question. The answer is surprisingly kind of no, but it's a little surprising as to why. So let's say I do that there. Let message equals greeting over here. It actually just straight up can't move out of greeting. Oh, this is for another annoying reason. Let me go over here. Closure let message equals greeting, like this. We should see that this is let underscore this equals that. Check FnOnce of F. I'm not going to get nerd snipe too hard here, but I'm just going to quickly double check FnOnce. Let X check FnOnce of X. Yes, this is what I expected. A FnOnce closure found unit. Oh, right. Yes. Yes. Oh, right. Yes. Hang on. Yes. Oh no, but they're all FnOnce. That's kind of annoying. I want to check FnMut. And then this only implements FnOnce. Okay, yes. It does end up moving. I was thinking of this. Oh. Okay. I've got to double check some stuff after the lecture, I think. So it seems like yes, correct, in that it is moving out. I was expecting some similar but slightly different behavior, which is why I'm like, oh, it's a little confusing. But also I'm in lecture brain mode, which often means that I'm missing rather obvious things. I'm gonna have a poke at that after the lecture again and do something on the forum probably. But from my quick thing there that was slightly surprising, yes, you're moving into the closure, and so the closure will only implement FnOnce. What I was sort of going to get to here is that all FnOnces are FnMutes. Sorry, wrong way around. All function pointers can be treated as an FN closure, just imagine a closure with no captures from the environment. All FNs can be treated as FnMut. All FnMutes can be treated as FnOnces. Right? The easy sort of comparison here being FnOnce, because the only requirement on an FnOnce is that it can be called at least, it can be called once, and all of these functions, right? Every single one of these can be called once. And so therefore you can treat any of these things here as a FnOnce and it'll still be happy. But you can't say treat something that's only a FnOnce as say an FN, right? It doesn't really work the other way. So a hot tip for good API design, there's some asterisks on this tip, is that you want to be as flexible as you can to the people using your API. Like, let's say if I'm designing a map function here, I want to be as flexible as I can. And so therefore you want to start with all the way on the left here. Like, if you can accept a FnOnce and it will work, then just take a FnOnce, because that means any closure that a user could possibly create, any function, any closure, whatever, your API will accept, and only move sort of rightwards as you need it, as you sort of have more complex requirements, right? So the thing that would drive you from a FnOnce over to a FnMut is if you need to call that function more than once. The thing that would drive you from a FnMut to a fun is if you need to call that function multiple times simultaneously, right? Like, you need to be able to call it, you know, at the same, like more than once at the same time, which is usually when you're getting into concurrency and stuff. That would drive you across to Fn here. And then moving from Fn to a function pointer is pretty, like, there's pretty specific reasons, mainly to do with things like limitations on traits and stuff and type parameters, or you need to know, you need to know the exact size and stuff like that. And yeah, because you get less and less ownership as you go. Sure, that's a perfectly reasonable way of thinking about it, is that here they can do whatever they want for the ownership. All the way over here, like here they can't take anything from the environment. Here they can only read from their environment. Here they can read and write, and here they can actually take ownership from the environment. So you want to start here and move rightwards. The big asterisk here is, you know, something you might want to consider is forwards compatibility. Is that, like, if you accept a FnOnce and then you go, actually, like, you've released the API, people are using it, and then you go, like, damn it, I actually need to call the function more than once. You'll then need to update your API to take a FnMut, and you might break a lot of people's code that was already existing. So there are some cases where you go, actually, I only need a FnOnce, but I'm going to accept a FnMut because I think I might need to call it more than once in the future. These kinds of things to, like, potentially think about. So what should MyMap take, right? Out of these options here, right? This FnOnce, FnMut, and Fn, we just, like, chose Fn because I said so. Like, at the beginning of the lecture, I was like, we'll use this one. What should MyMap, like, take? If FnOnce is the best and, like, Fn or function pointer are the worst, in terms of, like, you know, flexible API design, what should MyMap take correctly? Like, what's the correct level of function trait here for MyMap? I think it should take FnMut, since it gets called multiple times and can't take ownership of a variable more than once. Right, yes. So FnOnce definitely won't work for us because we need to call the function more than once. Like, some iterators might have 0 or 1 values, in which case a FnOnce could work, but we need to be able to support iterators with any amount of values, which includes 2 and upwards, in which case a FnOnce just simply won't work. So we need to step at least across to FnMut. Now the question is, are we happy with only calling it once at a time? And, like, in our case, there's a genuine discourse to be had here, in that the way it's written right now, we only ever call it once at a time, because next can only be called once at a time. We're guaranteed that because of the exclusive borrow on self, right? We know that I'll move myself back down now. We know that next can only be called once at a time because we have an exclusive borrow on self, and we can't have 2 exclusive borrows on self, you know, existing at the same time. So that's good. There is potentially something to say, like, so yeah, a FnMut should do for us because we're only ever calling this function here once at a time. Maybe in the future you go, actually, I want to make this iterator be able to do all the items all at once on a whole bunch of different threads for performance reasons, and then you might need to think about using a Fn, as we've done here. But for now, in our, like, single-threaded sort of quite specific context here, we should be fine to get away with a FnMut. Oh, true. If we allowed it to be called multiple times, we could async await it, which would be awesome. So let's switch this across to a FnMut. FnMut, and we'll find that our compiler error is gone. right? If I just do undo, undo, error, redo, redo, error gone, right? And let's try it out. Actually, let's uncomment the, oh, the list of code is uncommented. Great, let's do hello there, and you'll see they both seem to do the correct thing. So this closure here is in fact mutating its environment, and that's fine. Another great thing about the Rust compiler here is that if I screwed this up, like let's say I went, actually I can use a FnOnce and it will be fine, compiler error, right? Why do I get a compiler error? Because in order to call self.function, like in order to actually call it with this current item, I need to be able to take ownership of it. That's how the Rust compiler ends up proving that the function can only be called once. Because in order to call it, you need to transfer ownership into that call, into that function call, and ergo, like therefore, you only can call it once through that ownership system, as we know, right? It's this like whole parallel once again, or like, you know, how we were thinking about this example here. You can only call foo owned once. You can only call a FnOnce once, because like if you look at the trait, and this is like if you're really interested in like the sort of nitty gritty details and stuff, the FnOnce trait takes self owned, right? It takes self owned, whereas FnMut takes self as an exclusive borrow, and Fn takes a shared borrow of self. So this is like the borrow required in order to call the closure. And you can see that Fn requires FnMut, and FnMut requires FnOnce as well. And FnOnce has no additional requirements. And so, in fact, we could just sort of look at the signature here and go, well, next takes an exclusive borrow on self, right? Next takes an exclusive borrow on self. So, like, exclusive borrow is what I can do. That's like the sort of my best offer. All right, and it works. Pretty cool. So yeah, that's our like main distinction here between. So what should MyMap take? It should take a FnMut, as we've seen. That's like the least restrictive that it can be. Again, FnOnce is the absolute least restrictive. It's too restrictive for what we need to do as the API designer. There's sort of like a tug of war here. API designer versus person wanting to use the API, in that API designer wants to like give themselves the most flexibility, right? FN here being very flexible for the API designer, because you only need shared access in order to call it. You only need a shared borrow in order to call the function. But then it's very restrictive on the things that the API consumer is able to do. Like they can't say mutate their environment as part of the closure. So there you go. No, I want FnOnce. Like I want FnOnce because then I can do anything that I could possibly want to do. But then the API designer goes, well, if I do FnOnce, then I can only call the function once over here, and that won't work for me. So it's sort of this tug of war between the API designer wanting to give themselves the most flexibility and the API caller wanting more flexibility for themselves. And you want to find that middle ground that's the perfect sort of spot for both the API itself and the code that's calling the API. So, fun little bits to think about there. Awesome. Poor FnOnce hasn't had a turn yet. Time function. Yeah, let's do that. So we haven't had a chance to look at FnOnce at all, because like we used Fn, then we used FnMut. We haven't actually done an example with FnOnce. So what if I was making a function that was like that let you time some like closure or whatever. See, it just like prints how long the closure took to execute. So it wants to take in some function, and let's say it gives you back the duration, like how long that function took to run, right? So we might say something like let now equals instant now. Then, so this will give us the exact time that is now. Then we call the function, and then we say let duration equals now, like the time now after the function is being called, dot duration since, maybe now is not a good name for this, maybe before, duration since before. And then in fact, I'm just going to end up saying give duration back. So I guess I'll just say this code here. Give me the duration since this. Now this is going to say, hey, I don't know how to call f. What are you talking about? So I can simply say where f is some function that can be called once. Right, so fn would work for me here. FnMut would work for me here. FnMut would work for me here. But in fact, FnOnce is probably the best because it gives the most flexibility to them, and I only need to call the function once anyway. And so now any closure will work with our time closure function, and it'll be happy. And we can also use a bit of syntax sugar here to, save some characters with that Impl trait syntax, like this. Just say f is some type that implements the FnOnce trait, and do away, forget the generic type parameter. And this ends up basically turning into, it's very slightly different in the things that it allows you to do, but it essentially desugars into the exact same code that we just wrote, like this code here. The only practical difference is that if someone wanted to specify the type f with like that turbofish syntax we've seen a few times, it's not able to with this syntax. But that's fine in terms of function types because they're not going to be able to specify that type anyway. So great, we've got time closure. And let's give it a go. So I guess just around all of this, we could just say time closure of all of this. Oops, a little further. All of this. And then we'll say let the duration is equal to that. Println our implementation took duration. Like that. And does it work? Hello there. Our implementation took 20 nanoseconds. I think it's nanoseconds. Might be micro. I'm not a physicist. Yeah, 20, I think maybe nanoseconds. Microseconds. Okay, yeah. See, there's the proof. Our implementation took 20 microseconds. Fantastic. And it just works. Could we make it return a tuple with the result of the return value of the closure? Yeah, for sure. So we could say that this function returns some, has some type parameter t. The FnOnce can return any value t, and we'll give you back that t and also the duration of the function. So I'll say let t equals this, and then give back t and that duration. And then we could say, I don't know, return 42, let return value and duration equal this. Our implementation took that and returned return value. Hello there. Took 29 seconds and returned 42. So yeah, the code up here was any type t is fine. We don't have any, we don't care about what this t is. The FnOnce returns that t, and then we'll give you that t back. And again, if we don't return anything from this closure, that's fine. That's perfectly fine. This will just end up being unit, right? And if we change this to a debug print, we can even print that out. And it's just going to say and returned unit, returned nothing, essentially. So we're not limiting people by introducing this change. That's actually a fantastic change to make because it doesn't stop anyone, from using the function. It doesn't restrict anyone away, but it adds more information for the user to use. So that's a very nice change for sure as well. Cool. That's honestly most of what I wanted to look at in the lecture today. I think that's the end of our slides. Yep, that's it. Slide 21. And we're at 54. How incredible. In terms of what the different, I guess I can show you this as well now. The different types of closure captures essentially just change what this looks like. So this, if we had a FnMut that was like mutating something in the environment, would look like a reftic a mute f32, and then would impl FnOnce of @mute self. And so now, because it has exclusive access on self, it can then mutate self.borrowFactor, right? It can, you know, you get exclusive access to self, which means you can get this access to, you can mutate through this exclusive borrow in self, and then you can mutate the environment through that. So that works quite well. This needs to be @mute. And then this also needs to be, wait, I changed the wrong one. That's over here. Yeah, great. So this works fine. And then if you were making use of moves, this would have no capture instead. This would just be an F32. This would be, oh, sorry, did I write FnOnce here? I meant to write FnMut. This would be FnOnce. This would be self. And this would be the owned value factor. And so that's essentially what the compiler will turn all of these different cases into. Oh, another thing that's worth noting is that what if let's say I had, I made a closure and I captured one thing in the environment, like I captured a whole bunch of stuff from the environment. Some of the stuff was shared borrows, some of the stuff was exclusive borrows, and like one or two things I actually took ownership of. What do you think it will, what do you think that closure will implement in terms of the function traits? Anyone in the chat want to have a crack at that? So I have a closure, a whole bunch of shared stuff from the environment, some exclusive stuff from the environment, and also takes ownership of one or two things. What function traits will that closure implement? FnOnce, since the own stuff won't be available for another call? Absolutely. Yes, absolutely correct. Actually, I'm not going to be able to change these. I'm not very good at VS Code. So like if I had a whole bunch of stuff here, and I said let x is a closure, and then it goes like let a1 equals, you know, a shared borrow of s1. So it takes a whole bunch of shared borrows of some stuff like this. It takes in some exclusive borrows, S5, S6, S7, right? And then it also takes a couple of them by ownership, S8, S9. Let's just leave S10. Who needs it? Then what will this closure implement? Will only implement FnOnce. And I can do a cheeky little check here by just saying function check if FnOnce, f is Impl FnOnce, like that. Check if FnOnce, check if FnMut, check if Fn, and FnMut. There we go, like this. I can then say check if it's FnOnce, x here, and you can see it still builds, so that's fine. Check if it's FnMut of x, and the error appears up here. Essentially, this is to do with like how the types line up. I could no, it's still going to infer through a scope as well. Sadly, it's a little tricky. This is to do with Rust's particular type of type inference. The fact that the error comes up here as opposed to down here. But you can see once I check if it's FnMut, it's no good anymore. It was only FnOnce because it takes this ownership. If I comment out the ownership parts, then it's happy, but I've just moved out of X, so you know it's happy. If I check if it's if it's Fn, then again we get this error because it's capturing some exclusive borrows, so it can't be an Fn. It can only be an FnMut. Comment those out, and now everything's happy again. So it's a neat little trick to sort of check what kind of function traits a particular closure implements. Cool. I mean, yeah, I'm just like sort of poking at little bits and pieces that that's sort of coming off the top of my head, but that's all I was sort of looking for content. So I'll once again, as usual, I'll field questions as long as everyone has them. Yeah, field as many questions as long as you want to keep answering them. But otherwise, thanks for coming to the lecture. Hopefully we've learned a little bit, and we've got some background on using some function traits and closures and all that. We've made a map function that's basically, you know, pretty interchangeable for the with the standard library. You know, it's looking pretty good. What's assignment 2? You're gonna have to wait until sometime towards the end of this week or very early next week for that one. I saw some people were like, "Oh my gosh, we've hacked in and we found the assignment through like given stuff." That was there, you know, as when we were still booting up the course. Yeah, nice try. Nice try, but not quite. I guess one thing we can do while I'm just waiting for any questions. So again, we'll call it the end of the lecture. Thank you everyone for coming. I'll do the thing where we actually put MyMap in like the stud iterator, because that seems kind of fun to finish off with, so that we can actually call. Let's get rid of the time closure just to get rid of some of the cruft. So we can actually call it like this: names.intoiter.mymap of that. That seems like a nice little thing to do. So think of any questions. Otherwise, I'll do this for anyone who's interested in that. It's basically just going to look like trait MyMap extension defines this function here. With these bounds here. Like that. Then we say Impl for any I MyMap extension on for that I where I is an iterator, and the way we do that is like this. This I is already used, yep, so we don't want this. We don't want oh, sorry, I'm gonna have to get rid of the I parameter off this. So MyMap extension is going to be generic over some iterator type. MyMap extension of that iterator. And what are you upset about? You're upset that into iter found the following rules. Functions must have a self parameter. What have I done? Oh, I missed the self here. Right, yes, instead of this being iter I, this is now going to be on an iterator itself. So we can actually just do self. Actually, so in fact, we don't even need the iterator here. That's going to, that might piss off our bounds down here though. This is going to be self. This is going to be iter is self. Okay, and that's happy now. The scary thing of taking this I off is then I have to deal with these bounds down here, and it's, yeah, things are going a little nasty. I think, could you take this I off? You might be able to take this I off, but I'm not going to do it in the lecture because this should work for now. And yeah, now I've got names into iter.mymap. Hello. Yeah, cool. So that's a little extension trait trick there. Essentially saying define the function in this little trait MyMap extension. If you're using it elsewhere, you're probably going to want to make that public as well, which it's now really upset about because this struct here is not public, which it now is. And then say implement for any iterator I, this extension, which shows you how to call that function on an iterator. And so now whenever I have an iterator and Rust can see this trait in scope, which if we're in a different thing would just basically look like, you know, importing the trait like this, you know, then it'll happily just use .mymap like that. So that's pretty cool. All right. I'm not seeing any other questions. So unless anyone has any questions about this last little, you know, last little additional thing that I did here, we'll start to call it an end. So is using Rust format and its default settings a hard requirement for the assignments? I ran on my assignment one, but I wasn't a fan of a few of the formatting changes that made another random question. I am very much in that same opinion space as you. There is a subset of people who strongly believe that, you know, code should be like always run through an auto formatter. And there's very good arguments for that in that it enforces consistency. You know, two people might have different ideas about how code should look, but still, and both be correct and still be upset about the fact that some people might write code some way and some people might write code another way. You know, in the face of all of that, when I'm working in a code base of my own, I still tend to prefer to do my own formatting. But I can see the appeal of enforcing, you know, Rust format or like any kind of standard format in, you know, larger projects and you know, if you're looking at the industry and stuff like that. With all that being said, we are perfectly fine with you applying your own formatting. I think we have, I'm in the tutor mode. Assignment 2 leaked. Let me just hop out of there before I make a mistake. With all I said, I think we actually mentioned, let me just double check we said this here. Formatted with Rust format. Yeah, okay, maybe we may not have said this, but I'm going to say it because this was, you know, originally part of the plan, is that is that if you choose to just like let Rust format your code, then we will not deduct any style, like this mechanical style here. There's then like no problem if you format your code with Rust format. And in fact, like I think you know, even Clippy in this case as well could maybe fall into this bucket, but not quite as keenly. If you choose to deviate from Rust format, it's sort of like at your own risk. But if it's like a sensible decision, then we're not going to penalize you on that. If it's like, oh, I really wanted to, you know, line these function calls up, like call some function and it has like param1, param2, param3, and then you're calling this function like 4 times in a row with like things that are like slightly different lengths and some that are like a little longer. I personally like to do things like this and like line it up so you can see here's where they're the same, here's where they're different kind of thing. If you did something like this and Rust format goes, no, they should all be like, you know, one space afterwards, you know, we wouldn't penalize you for something like that. We go, yeah, that's a fine decision that you've made to go against Rust format, and we're not 100% enforcing Rust format for the assignments. But if there's some sort of particularly egregious style decision that Rust format would have fixed that you chose, then we sort of reserve the right to mark you on that. But we're sensible is what I'm sort of giving you here. Okay. Told us to use Clippy, forgot to test the quests. Time plan of sleeping. Okay. So yeah, that's basically where we're at with that. The same rules will apply for assignment 2 as well. The thing I was going to say with Clippy is sometimes Clippy is like, most of Clippy's lints are pretty good. In general, Clippy's lints are very good. But occasionally it's like, it might be like overly restrictive or overly pedantic about certain things. And like, again, we'll maintain a certain sensibility for this kind of stuff. But yeah, we're not sort of looking to just take marks away from people for no good reason, essentially. Clippy was the most helpful linter I've used. Ah, okay. That's nice to know. Clippy really doesn't like unwrap or. Does it not like unwrap or when you're calling a function inside the or? Out of interest? Loves an else on that. That's it's actually like a smart lint, in that if you have let x be some 42, and I want to say x dot unwrap or actually 42 is a bad idea, string from hello world, unwrap or another string like you know, goodbye world. The funny thing with unwrap or is that it will always construct this string. It'll always go and do the malloc and create the string and copy the bytes in, regardless if it's sum or not, because it needs, like, Rust doesn't see this function as special or anything. It just sees that it needs this parameter, so I'm going to give it this parameter. Whereas if you do or else, you just throw like a closure in front of it, and unwrap or else will only actually run this code in the case where there's a none, like in the case where the unwrap ends up failing. And so you only end up sort of paying for this string in the case that you need it. I do believe that when you're not calling a function, like if I already have this string elsewhere, if I just do unwrap or s, I don't believe Clippy will lint that. It'll go like, okay, well, you're not calling a function, so it's fine. But where it sees that you're calling a function anyway, it's like, okay, well, you're already calling a function, just like pass the function into unwrap or else so you don't pay for that. And there probably won't end up being, any additional overhead in, this function anyway, in like making it a closure, because again, we've talked about LLVM's inline heuristic being yes, in that it'll just find the code for string from blah and just paste it straight into this, function anyway. So it's actually like pretty cool lints and stuff that it'll give you for that kind of stuff. Some of the suggestions were frustrating when telling you to remove boxes and stuff that were there to make the interface nice for other parts of the code. Yeah. There is also like you can toggle things about Clippy. In that you can say things like, how do you toggle Clippy stuff? It's like allow, I think, allow Clippy : is the kind of thing. So if you go Clippy, shut up about like borrowed box or something like that, then you can just say allow this pattern in all of my code here, and Clippy will stop complaining about it. It goes the same for other compile errors. I often do allow unused when I'm in the lectures because to not clog up warnings about things not being used. Why does unwrap or exist if underscore else is better? Because sometimes there is no overhead in the unwrap or, and the overhead of a function would be just like sort of senseless. In the first example where I was writing a bad example, in the case of something like let x equals sum42, x.unwrap or 123, right? There's no allocation, there's no function doing a lot of work going on here anyway. It's just passing like a byte to the function. Whereas if it told me to do unwrap or else with a closure, now I actually, like, the overhead in having a function there and having to call it is slightly more. And like for a programmer, like looking at this is also just less clear probably than simply this. So that's generally why. Rust often lets you choose convenience or performance, and or like, lets you pick and choose where the performance makes sense and stuff like that when you're writing it. I had an unknown tile type which became unused when I implemented everything. Instead of deleting it, I allowed unused, since that way the code is there for future. Cool. Alrighty. So yeah, any more questions? Any other questions before we cap things off? Naturally, thanks again everyone for coming. I hope you enjoyed. Okay, not really seeing much more in the chat, so thank you again, everyone. We'll see you in the workshops. We'll see you in the workshops this week. We'll see you in the lectures next week when we get to finally talk about concurrency, which Rust makes, Rust has some really very cool things to say about concurrency. So we'll see you all then. And yeah, bye for now. See you later.